Hi students, welcome back to DSP online lectures. Hope you have gone through the previous lecture, that is reviewing the transform analysis concepts that we have already discussed in the classroom. Now in this lecture we will further continue our study of transform analysis of LTI systems, and the specific topic of our study for this lecture is inferring poles and zeros from magnitude response. Okay, let's go ahead. Okay. Uh, so what we are interested is in studying, as I mentioned, inferring poles and zeros from magnitude response. In fact, to be more precise, it's the square of the magnitude response. So to get into there, let's start with using the notation of let P of e power j omega is equal to magnitude of h of e power j omega squared. Okay. Yeah, in the class we had a little bit of discussion about whether this would be an energy or a power like spectrum. So you could see, had there been a summation here, that would have been an energy signal, but this essentially is a power signal. You notice that we are computing it for each value of omega, right? So how can we write this magnitude? You already know it. This given this could be a complex number, you could write it as h of e power j omega, right, multiplied with h conjugate of e power j omega, right? This can also be, as I mentioned right now, this can also be called as power spectrum of a given signal. This can also be referred to as power spectrum, right? Before I do further, so here we also assume throughout this lecture, we'll also be assuming that our h of n is a real signal. H of n is real. Okay, so here we will be making use of a couple of results that we have earlier derived while discussing about the DTFT. So I leave it to the to an exercise, as an exercise to you, those things, but I'll write them out and you work it out yourself. So the first one I want you to work out is the first exercise for you is prove that if the DTFT of sorry, if the DTFT of x of n is x of e power j omega, right, what would be the DTFT of then? Okay, anyway, I'll give you the answers so that it becomes easier. So you prove that then the DTFT of x of minus n would be equivalent to x of e power minus j omega. You start, it's a very simple one actually, but anyway, as a practice I would give it to you. Okay, I'll also one more exercise problem here. These are the results that we would be using in our further pursuit of this problem. The second exercise for you is prove that if x of n is real, then x of e power minus j omega is equivalent to x conjugate of e power j omega. You please do it for yourself, these two exercises. So what the second one means, it essentially the magnitude spectrum will be the same, and it's essentially it's a complex conjugate. That's what it could happen for omega and minus omega. Anyways, I leave that part to you. Let's come back here. So where we would be using these results in our analysis in this case. Then how can I write this out if I make use of these results? This is h of e power j omega. You could see here h conjugate of e power j omega from the second exercise is equivalent to h of e power minus j omega, right? So from the second result that you are going to prove, you could write it, and then you go to the first exercise. Okay, so then its dtft is nothing but h of minus n. So first we will write the equivalent expression in the time domain. That's what we will do now. Equivalent expression in time domain will be now, let's take an equivalent expression there. You could see here then p of, let's represent that with small p. P of n is equivalent to h of e power j, multiplication in the frequency domain is equivalent to the convolution, and for h of e power j omega, this is h of n and convolved with h of e power minus j omega, first exercise result, that's equivalent to h of minus n. Okay, this is the result that we have arrived at. Again, as I mentioned, the assumption is that h of n value is real. This is our assumption here. So that would eventually, so with that assumption, I could write it also as h of n convolved with h conjugate of minus n. Okay, yeah, we are actually interested in the z transform analysis. So for that we started with the Fourier, we went back to the time domain, and now we take the z transform so that we will get the equivalent expression in the z domain. Okay, again we will be using one more result here, which we already had the background we covered in our classes on z transform. So please work that as well. I will just mention you the result here, you please work it out yourself. So as the third exercise here, for example, prove that if the z transform of x of n, the z transform of x of n is equivalent to x of z, then the z transform of x conjugate of minus n would be equivalent to x conjugate of 1 by z conjugate. And yes, this being a z transform, we need to mention the ROC also. Assume that here the ROC is R subscript x, and then this would have an ROC of 1 by Rx. So you prove this as well. Okay, in this class we anyway will directly use this result here. So that implies you apply z transform for this expression now. That implies applying z transform would result, again capital P I use here, is equivalent to h of z. Okay, from the result in the exercise C, anyway that convolution in the z domain is multiplication. From the exercise 3 you have here the expression of h conjugate of 1 by z conjugate. This is a very key result here for analysis of the inference or inferring the poles and zeros from the magnitude response for the z transform. Okay, again as I mentioned, a very important assumption here is h of n is real. Actually this is not explicitly mentioned in, by the way, in Oppenheim and Schaffer, so it took quite some time to figure out and arrive at this derivation, which is not as such is given in detail in the textbook. Okay, anyway we'll continue with this. So notice now the question is, you are given now, what is the problem that we are trying to address here? You are given P of z, and from that can you say the pole and zero plot, pole zero plot of h of z. So to do anything similar to that, let's first take the expressions as I mentioned in the previous class. We consider the rational transfer functions, right? I directly take the result from the previous class and how it looks like. A rational form would be b naught by a naught, right? And there are, in the numerator, k is varying from 1 to m, 1 minus ck z minus 1. In the denominator, k equal to 1 to n, 1 minus dk z minus 1. Okay, now let's write the expression for h conjugate of 1 by z conjugate. It's very easy. For example, you take one value here, like in that multiplication, 1 minus ck. Okay, let me write that z minus 1 as 1 by z, for example. Now if what I need to do is, the z you replace with 1 by z conjugate. Okay, and then you take the conjugate for the whole stuff. So that would be 1 minus ck, right, and z conjugate it will result, and you are going to take whole conjugate for that. Okay, this is for h. So that would result in 1 minus ck conjugate z. We'll use that here right away for all the terms. Now it would result in b naught by a naught, k varying from 1 to m, 1 minus ck conjugate z by pi varying from 1 to n, 1 minus dk conjugate z, right? Now let's write the expression p of z, which is multiplication of both these terms. From that we have p of z equal to b naught by a naught whole square. In the numerator, k varying from 1 to m, 1 minus ckg minus 1 into 1 minus ck conjugate z. That all over. In the denominator, now you have k equal to 1 to m, 1 minus dkg minus 1 into 1 minus dk conjugate z. Okay, this is again a very important expression. Right? Okay, so let's make a quick analysis of what are the poles and zeros of it. Okay, so for that, let's consider one of these representative terms. So for that, let's consider take 1 minus ck g minus 1. Okay, this I could, similar to the previous class, you could write it as z minus ck by z, which means it has a pole. Well, it has a pole at z equal to 0, and this root, since this being in the numerator, corresponds to a 0 at z equal to ck. And now you take the another term, ck conjugate into z. I could write it as, let me take that minus ck conjugate out. This would be 1 minus, then it would be g minus, if I take that out, this would be g minus 1 by ck conjugate, which implies it has a 0, right? This being the root, this being in the numerator, it has a 0 at z equal to 1 by ck conjugate. Anyway, in the first 1 minus ck into z minus 1, we are not interested at poles or zeros. It is not of our focus for poles and zeros of g equal to 0. This we already discussed. For example, if m is greater than n, that would eventually you will have m minus n poles at z equal to 0. We are more interested in the non-zero roots of this thing. Anyway, the new term that got added up because of this h conjugate of 1 by g conjugate doesn't contribute to as such any poles or zeros at z equal to 0, right? So you could do a similar analysis now for the denominator of it. For example, the first term would contribute to a pole at z equal to dk and also a pole at z equal to 1 by dk conjugate, right? So we will make a few more observations from here. Let's see, let's have a more closer look at this expression for p of z. So first thing, where are the zeros of p of z are at what all places does it have zeros? At c, so this k varying from 1 to m there, so you have it at c1, 1 by c1 conjugate, c2, 1 by c2 conjugate, and so on. You have m such terms, right? So you have cm and 1 by cm conjugate, right? Second, let's take a look at poles. Poles of p of z are at d1, 1 by d1 conjugate, d2, 1 by d2 conjugate. There are such n terms, dn, 1 by dn conjugate. Of course, there are plus some possible poles are zeros at poles are zero depending on the m and n values at z equal to 0 also would be there, right? Then another, these are almost obvious. So another important observation is that poles and zeros, let me first mention that and then we will discuss that. Poles and zeros of p of z are mirrored across the unit circle. This is a very important point here. You take a look here. Whichever the magnitude of c1, let it be as long as this is less than 1, you have that inside the unit circle, and that is 1 by c1 conjugate would go out. So let's take a real value. For example, if c1 equal to 0.1, 1 by c1 conjugate is 1 by 0.1, that's 10. And similarly the same thing applies. You could see that these are all mirrored across the unit circle. Okay, so maybe this would become more clear if we just draw a pole zero plot for one of them, for example h of z, and then take a look at the pole zero plot for p of z. That's what we will do now. Okay, so let me draw here. Let's draw the pole zero plot now. That makes things clear. The real axis, imaginary axis, the unit circle, assume that your h of z is having let's say a pole here. Okay, pole here, let's call it as p1, and then I'll notice that although the h of n is real, these values could still be complex, but it has to be complex conjugate poles. When you will be having that complex conjugate pair. Okay, that result you please work it out if that is not very obvious to you at this point. Okay, so let's call this another, so a pair of complex conjugate poles, let's consider here P2 P3, let's say. Okay, yeah, for the time being 3 are good enough here. Let's consider now some zeros of this function also. Okay, assume that, well, some 0. Okay, let's take a 0 here, and then again let's take a pair of complex zeros as well. 1 0 here, 1 0 here. Okay, so these are whichever is there in this color, these are for h of z. Now what would be for h conjugate of 1 by z conjugate? The poles, where do they lie? Now 1 by, this would introduce this being real. For example, 1 by, let's start with the poles you have at 1 by p1, assume 0.9 or something like that, this, so okay, 9 by 10, you will have a, this would introduce a pole here. Okay, now this, let me draw a line here. This angle would remain same. Okay, this would introduce a pole here. Yeah, the magnitude it could yeah, maybe let me write a bit far here. Yeah, somewhere here, right? And similarly here, somewhere here. Okay, these are the zeros that got introduced because of poles that got introduced because of 1 by z conjugate, right? So now let's come back to the poles. Okay, assume is 0.1 somewhere here, 10, right? And here also this would introduce a a 0 here, right? Definitely this would introduce a 0 here. Okay, this whole plot is for p of z in the z plane. Okay, this is your z plane, right? Then the question would be, what we started with, our purpose is, can we infer what would be the transfer function given p of z instead of being given the right away the h of z. That's what pole 0 plot of magnitude response is given, then can we get the pole 0 plot of h of z? That's the question, right? So well, we know that which are the pairs, only one of them could exist. For example, let's write down the list of pairs here. Okay, so before that, let's give names to these things as well. Say for example, let me call, where is our z0 there? Okay, I didn't given any name. Okay, so let's okay, 1 minute. So let me, for example, write it as z0. 1 minute. So let's call this as z0, this as z1, this as z2. Okay, now what has resulted, this p1. Okay, we were starting it from 1 subscript there. Let's do the same thing just for the sake of consistency. Let's do the same here. Okay, so this is, let's call it as z1, z2, and okay, this has gone in our whole process. There is one more here, this is z3, right? And what did we get here now? This z1 has given us z2, z2 is, okay, z2 is z1, z2, z0, z1, z2, z3. Let's call it as z4. Let's call this as z4. This, let's call it as z5 and z6. Okay, and then anyway, this is p1, p2, p3. Call it p4, p5 and p6. Okay, we'll come back here now. Right, so which are the pairs here? Z1, okay, Z1 and Z1 and Z4, then Z2 and Z5, similarly here Z3 and Z6. Similarly, if you look at the poles, you have P1 P4, right, P2 P5, P2 P5 and P3 P6. Only one of them could exist. Now suppose if I give you the information, additional information, that this is a causal unstable system. Assume H of Z is causal and stable. What can we say then? The poles and zeros of it should lie, no, nothing to do with the, we are not talking about the inverse system. All the zeros should lie, all the poles should lie inside the unit circle. See this, as I mentioned, this is an important observation here, that the poles and zeros of P of Z are mirrored across the unit circle. So what could we say then? We know for sure that this H of Z would for sure will have 1 minus, so it will have then P1, P2, P3, not the other things. So 1 minus, you know for sure here, you have 1 minus P1 into Z minus 1, 1 minus P2 into Z minus 1, and 1 minus P3 into Z minus 1. Yeah, these are of course complex conjugates, so I could in fact use P2 conjugate there. Okay, so those are the ones. And then then it could take either as zeros. There are, what are the possibilities here? Possibilities for zeros are, for example, it could take Z1, Z2, Z3, right? Or instead of Z1 it could take Z4 and remain the same, okay? Or else it could have taken, there are multiple combinations here, okay? It could have taken Z1 the same, Z1 being the same, and then let's say Z5, Z6 and so on. There are different possibilities, but now on the other hand, there are limited possibilities of what all values it can take here, okay? And then we already discussed the inverse system. Suppose if I know that its inverse is also causal and stable, then I could already narrow down to here Z1, Z2, Z3, and I could right away infer what are the poles and zeros of H of Z given P of the pole zero plot of P of Z here, right? Yes, we will anyway further discuss it, and you will understand the importance of the study once we move on to the next couple of classes. But I hope still here it is clear. So I repeat here, you are given the H of Z, P of Z. So you have mirrored poles and zeros here coming from the H of Z gets mirrored, and you have double the pairs are there now, and among that you have only limited number of possibilities, and depending on the characteristics of the system you could now narrow down to a minimal number of some possibilities of values of poles and zeros that it can take. For example, if had it been Z1, Z2, Z3, okay, you could have written here, for example, 1 minus Z1 Z minus 1 into 1 minus Z2 Z minus 1, 1 minus Z3 Z minus 1. Of course there will be a multiplication factor which we are not worried about it at this point of time. Okay, so yeah, hope that is clear. Then let me conclude this by giving you one more exercise. You please work it out before the like having one flipped class conference call session. Okay, so let me give you one more exercise here. You please work it out. Exercise, so I think this is fourth one, correct? Yeah, this is exercise 4. So let's say let your let me call it as h1 of z is equivalent to 6 plus g minus 1 minus z minus 2. Okay, this is given. So first part of your exercise is, so you are given the h of z. Okay, you specify all possible. By the way, is it causal or non-causal? How do you know that? You just do h of n. These are all delayed versions, so essentially this is a causal system. So I want you to specify all other possible causal systems also. Causal systems, right, that have the same magnitude response. That have the same magnitude response as h1 of z. You please work it out. It's not difficult. All you need to look at is you factorize that. Okay, you have a couple of zeros here, right, and for that you look at the complex conjugate systems, and again all that you need to do is pay attention to the normalizing factor here. For that again you just take a look at its magnitude at, let's say, omega equal to 0. That should be enough for you to figure out what are other possibilities, and finally you write them, all those possible ones, you write them as again polynomials here. Okay, so as h of z, of course they will not be having the same phase response. Okay, so although having a different, although this resulting systems, although having a different having different phase responses, that doesn't, let's not worry at this point about the phase response. Okay, let's not worry about, although having different phase response. So that's the first part of it. Okay, then what you do is you use any of the tools like MATLAB. Just this will be a very simple few lines of code. All I want you to see is to cross check your answer also. This will help. Plot the magnitude and phase responses of all those equivalent systems. Okay, equivalent in terms of the magnitude response. So of course you should be obviously looking at the same response there in terms of the magnitude, but it's the phase that would vary here. So the last one, you make an observation that among all those systems, which is the system that is having minimum phase value? All those systems, which one is having minimum phase value at all frequencies? Okay, and you would observe that this would in fact corresponds to a system that has all its poles and zeros inside the unit circle, and that's not a coincidence there. Okay, by the way, just one point, we are everywhere saying it all possible causal systems, but it's obvious it would be there as 4. I'm just giving you as a hint because that would help you while you're working on. Okay, so that's all for now, this class, right? Any questions? If you have it, please go through it carefully. If you have any questions, we will discuss in our conference meeting. Okay, yeah, thanks a lot. Yeah, have a great day. Bye.